All right, so I believe I can just make a new project here from file new. Yeah. All right, so we're just gonna make a new project here and make a new HFSS design here. I'm gonna save this one here. All right, so again, I forgot to mention this in the last one, but you want to go to HFSS and make your solution type terminal. Make sure that's terminal. I forgot exactly why that is, but it has something to do with your voltage source. Evan, do you happen to know?
Sorry, could you repeat that once more?
Yeah, like we want to go into HFSS and make our solution type terminal. Do you happen to remember why that is?
I just know that it makes it easier when you're setting up the port. It just makes it easier to define how you're basically setting up that port. I think if you do modal, it's just kind of more complicated. I'm not exactly sure though, but yeah, you always want it to be in terminal for at least this for our class and design project with Dr. Jackson.
Yeah. All right, so now that we have our new project, let's just define some of our variables. So we know we need a B1, which is our initial distance. So let's just call that 1 millimeter for now. And then we need a W, which is our initial width from the inner edge to the outer edge. So let's just let's make that 0.2 millimeters for now. Let's just use B2. B2 is just a like a transition variable. So our calculations aren't too complicated. So that's just B1 plus W. We need our spiral factor, of course, A1. Let's just make that 0.1 for now. And then what else do we need? We need our number of turns. So we need turns. Turns, let's just say, is 2.4, something like that for now. All right, now let's get into making our independent variable. So we need TS1. TS1 is just 0. And then TE1. TE1, of course, is 2 times pi times turns. And then we also want to specify R1. So that's where the outer edge ends. So the magnitude at which it ends. So R1 is B2 times exponent of A1 times TE1. So that's R1. And then we also want to specify TN2. TN2, so that's TE2. TN2, if we remember that formula, is the natural log of R1 over B1 all over A1. So I believe we just use log again, R1 over B1 all over A1. Oh, okay, so they don't use log anymore. They use ln for natural log, and they changed it for us, so that's nice. All right, so I think that's all we need for now. Let me save this again. So I'll just save this as spiral 2. All right, so now let's get into plotting our spiral. So we're going to go into the create line tool. All right, so our X, so we're going to start with the inner edges. So it's going to be B1 times exponent of A1 times underscore T times cosine of underscore T. Then Y coordinate is going to be the same thing, except it's going to be sine. Then our Z, we're just going to keep Z at 0. Start underscore T is TS1. Start is T start 1. End underscore T, and this is for the inner edge, so our end is going to be TE2. And the number of points, let's just say it's NP, and then 200 points. And there we go. We have our first inner edge. So let's make our second one. And to do that, we just make X and Y negative. So X is negative, Y is negative, and there we go. So we have our two inner edges. And again, I'm going to name everything. So I'm going to call this arm1 underscore IE for inner edge. And then this is arm2 IE for inner edge. All right, so now let's make our outer edge. And to make our outer edge, let's just make this B2 instead. So this is B2, and since this is the outer edge, we're going to change our NT to TE1. Hit OK. So we have our first outer edge, and then our second outer edge, just make X and Y negative. So this is negative, this is negative, and hit OK. So this right here, we're going to call this arm1 underscore OE for outer edge. And then this is not right here, but right here, this is arm2 underscore OE for outer edge. All right, so this is going to be our taper design. So now let's get into making our circular pieces. So let's just go here. Again, our circular pieces is just going to be R1 times cosine underscore T. And Y is just going to be R1 times sine underscore T. And then our T is going to go from TE1 to TE2. All right, we can see we have it right here. Let's click OK. And that's our taper design right now. So I'm going to call this arm1 underscore taper. And then let's make our second taper. We just make these negative here. This is negative, this is negative. All right, click OK, and we have it right here. So this is arm2 taper. Looking good so far, Evan?
Yep, it's looking good.
Yeah. All right, so now let's just make our inner bounds also. So that's also pretty easy. Y is just going to be 0 throughout. Our X, if we start at 0 and go to 1 for our T variable, then we can make X. We can make X B1 plus underscore T times W. So that way when it's 0, we just get B1, and when T is 1, we get B1 plus W, which is B2, of course. So we click OK. We have it right here. And
so yeah, this shows the importance of why it's really good to label as many parameters as you can, because how you're designing this right now, if you were trying to put in each specific value, this would just be, really painstaking.
Yeah, and we only need 2 points since it's just a straight line. So let's just make that 2. All right, so let's make our other inner bound. So it's just going to be the same thing except X. Let's make this all negative. So negative in parentheses. Start T is 0. Number of points is just 2 since it's a line. And click OK. And there we go right here. Right here and right here. So this first one here is arm1 underscore IB for inner bound. And this one right here is arm2 IB for inner bound. All right, so now that we have that, yeah, so now everything is pretty much bounded. So let's see if our cover lines work. So let's take all of arm1 here. Let's let's union everything. Not that one, this one here. Let's unite. This one here, let's all unite. And now let's see if our cover lines work. So we're going to right click, go to edit, surface, and cover lines here. And it does work. We can see we turned that into a plane. Let's take our other lines here, go to edit, surface, cover lines. Very nice. So we have everything as a plane now. Let's make arm 1 black right now. And let's make arm 2 white. All right. So now what we're going to do is we're going to make our feed here into the center. And this is pretty much the same thing that we did for the Archimedean spiral. But I will go over it again. So we just make our rectangle. And I want our rectangle kind of look like this, but let's make sure all of our dimensions are right. So the X size is going to be B1 plus 0.5 times W. And then our Y size is just going to be W. So first, let's center this to make so we know how much to move it. So again, to center this, and then I'll actually just call this X underscore feed here. So X underscore feed is that. And then we want to center this. So again, to center, we just make it negative at the X parameter over 2, and then negative the Y parameter over 2, and then all at 0. So now we have it centered, and we want to move it X underscore feed over 2 in the positive X direction. So we just take this and we add X underscore feed over 2, which is the same thing as just putting 0 here, but this is just to help understand how you're moving it when it's sent after it's centered. So now we have it right here where we want it. All right, so this is called or what did I do here? I accidentally clicked this and it did something. Let's cancel there. Yeah, I accidentally checked these here. So this is arm 1 underscore feed. So we have that. Now let's make a feed for the other spiral arm. So again, this is going to be X underscore feed. Y size is W. Let's center it initially. So it's going to be negative X underscore feed, negative W over 2, 0. We have it centered. Now we want to move it X underscore feed over 2 in the negative X direction. So we're going to take this, put this in parentheses. We're going to do minus X underscore feed over 2, like that. And we have it where we want it to be. All right, so now, again, just like the Archimedean spiral, I like to have a curve here. So we're just going to make a circle and move it so we can get a nice curve here as opposed to something very angular. So let's just make our circle here. The radius is going to be 0.5 times W. And we're going to center it initially. So it's centered. We need to move it just X underscore feed. That's its position. So position X underscore feed 0, 0. And there we go. Now we're going to have this really nice transition curve from the spiral arm to the feed. And let's do that for the other side. So make our circle. The radius is going to be 0.5 times W. The position is going to be negative X underscore feed. Hit OK. There it is right there. This circle 1 is arm 1 underscore circ. The other circle is arm 2 underscore circ. All right, so now that we have that, let's do some more uniting here. Oh, also this rectangle, this is arm 2 underscore feed. So that's arm 2 underscore feed. Let's do some more uniting. So we have our arm 1 and our arm 1 spiral arm, our arm 1 feed, and our arm 1 circle. Let's unite all of those. Looks pretty nice here. Then let's do that for arm 2. Let's click unite. All right, everything is looking pretty nice. All we need is our source in the center here. So that's just going to be a rectangle here. Let's call this a source. Let's make that yellow. So source, it's just going to be a square. So it's going to be W here. Then W here. Position is negative W over 2, negative W over 2. 0 is just going to be centered. And there it is right now. So, and of course we have these this overlap here. We don't want that. So we're just going to we're going to highlight all of these. We're going to go to our subtract function. And we're going to move our arms to this side. So we're doing our arms minus the source. But we don't want to get rid of the source completely. So we're just going to click clone tool objects here. Hit OK. And now we can see there isn't any more overlap. And so now this is pretty much all we need in terms of construction of the spiral. Evan, what do you think?
Yeah, for the like copper taping basically on top, yeah, that's pretty much it. And then the substrate, you know, it's pretty simple to make, but yeah, for the spiral itself.
Yeah, so if we wanted to make make it into a cavity back again, so we
And
can
then,
take our,
yeah, maybe try too showing how it changes like as you change a couple of variables and like
oh
how
yeah,
easy it is to like adjust from there.
yeah, let me just, I'll show that. Let me make this substrate first. So this is substrate, let's say it's made out of FR4 underscore epoxy here. Let's make this blue and wireframe. And so create cylinder, let's say this is R underscore sub, which is 50 millimeters. And then the height is H underscore sub, for which for my case was 0.8 millimeters. Number of segments is NS, which we'll just say is 200 for now. Centered at the origin. So here it is, it's pretty big. So yeah, so again, this is a very robust spiral design. So the parameters you can change, you can mess with B1, which is the initial distance, W, which is the initial width, A1, which is their spiral factor. It's not confined to a function as opposed to the Archimedean spiral. So you can change A1, although you don't want to make it too small, or else you could get some overlap. Then you'll have to change that. So B1, W, A1, and turns is what it looks like you can adjust to get a different spiral. So for example, B1, we can make this like a 0.5 millimeters. Your initial width could be something like also 0.5. A1 could be like 0.12. And the number of turns could be something like 6.75. That might be too big even for the substrate here. Okay, so here's here's what I was talking about. We're getting a lot of overlap here. And so
yeah, and you could also adjust these values by just double clicking on the HFSS terminal design.
yeah. Wait, where's that here?
Like yeah, right there. If you double click
Right
on that.
here. Oh,
And then
yeah.
see below. Yeah, it pops up down there too. So then you could just kind of input them, click out, and then it will adjust like
Yeah,
on the
so
fly right there.
if we didn't want this overlap, we have to make our spiral factor much bigger, much bigger. So let's try 0.17. That's still not big enough. So let's try a 0.2. All right, we're getting there. Let's just try 0.3. There we go.
There you go. Nice.
Yeah, but this extends way
It's
past our substrate.
obviously, yeah, and it's huge. It's
Yeah,
ginormous.
so turns. So that's what I was saying, that equiangular spirals grow much faster than Archimedean. So let's just make this 3 turns. I think 3 turns is still way too big. 1.5 turns there.
It's fun to play with those. It's cool.
Yeah. I think if we make, and then B1 also has a significant influence over how you have to change the other parameters. So like if we make this go back to 1. Then we can make our spiral factor much smaller here. So maybe to 0.2. Yeah. And then we can increase the number of turns. So let's say like 3. That almost
Interesting.
fits. That almost fits on our substrate. So 0.2.5, maybe 2.8, a little smaller, 2.7. All right, that's fine for now. So again, our substrate is on top of the spiral arms. That's just because for my design, I had to get it fabricated and then turned it upside down to get a good connection with the balun. So if you wanted to make a cavity back, you could we can make our cylinder here. So this would be our cavity back or metal frame. Cavity back, let's say it's made out of silver for now. Let's make it gray. All right, and then it's we'll make the radius r_sub. The height, we'll get back to the height again. So number of segments is ns. All right, so we want to specify some more variables. So we want our h_cav here, which is the height of the cavity. Let's just say it's 8 millimeters right now. And then we also want the thickness or width of the metal frame, which I call w_mf, which let's just say is 1 millimeter for now. So now that we have those, let's make our cavity or the vacuum or air within it. So cavity, let's just make a cylinder like this. Doesn't matter, we'll change it here. So the radius is going to be r_sub minus 2 times the width of the metal frame. The height is going to be negative h_cav. It's centered at the origin. Number of segments is ns. Hit OK. And then the height of the cavity back is going to be negative h_cav plus width, the width of the metal frame. So, and then all negative like that. And then we can simply do the cavity back minus the cavity itself. So this is the cavity. So cavity back minus the cavity here, just do the subtract. And we don't want to lose the cavity completely. So let's just clone the cavity here. Hit OK. And now if we make the cavity, it's just a wireframe, black wireframe here. We can see now that we have our cavity back now. All right, and so that's pretty much all there is to the design part. There is also, you also might want to consider the feeding the spiral arms through a balun, which is probably going to be a tutorial for another time. But if you wanted to simulate this, well, you also have to assign the perfect E in the source. So take arm 1 here. We have to assign boundary and perfect E here. Hit OK. Arm 2, assign boundary, also perfect E. Hit OK. The source is going to be assign excitation port, lumped port. That's our voltage source. Let's just say arm 2 is our reference. So do that right there. Now we have everything in boundaries and excitations here. And now if we wanted to make an analysis, we can go here, add solution setup, auto. And then you can name your setup. You can make it balanced, higher speed or higher accuracy, whichever one you want. Change your sweep type to discrete. And then I like to do linear step. So I have to go from, let's say 1 gigahertz to 10, maybe 0.2 or 0.1 gigahertz step. So that's 46 points. That's all right. Then hit OK. And then you want to define your far field box, your radiation box for your far field parameters. So you just right click on this grid behind you and you can go to create open region and then just do the default stuff and that's pretty much all you need for to make an easy radiation box. And then, yeah, that's pretty much all there is to it. You can go to simulation, you can validate it, make sure everything does look good. And that's pretty much all there is to designing equiangular spirals. Evan, is there anything you want to add?
No, I think you pretty much got it all.
Yeah.
There may be more you have to do, like if you're adding a balun or a source, like he was saying, or a feed line. But it's basically the same idea and stuff. You'd have to assign it to an to excitation or a boundary, or depending on kind of what you're adding, or if you're adding a whole nother piece below it, like let's just say kind of like with my design, it has a reflector, so I basically have an entire another substrate underneath with more copper taping on it that helps kind of excite my antenna more. And
Yeah. Also, if you wanted to maybe like experiment with the excitation, you could go to HFSS, go to fields, and then go to edit sources. Here you can check on the magnitude of the source, so the voltage magnitude and the phase. So if you were getting to like what I was doing, like arrays, you can like change the phase of each source, but that's a little more in-depth, complicated, right?
yeah,
Yeah. But that's pretty much all there is to it for the equiangular spiral. So I really think there's a lot of potential for spiral antennas. Uh, I really think we can achieve more, like a better S11 parameters, better realized gain, better axial ratio, and that's all there is to it.
I hope this tutorial would be very useful for students in the future.
Yeah. All right. That's all for this one.